the break, we went through its representation, and now it comes to the fun part, at least for me. It's a very elegant constant propagation algorithm for Boolean problem, Boolean satisfiability problem, which is, in my opinion, is extremely elegant, and it's so simple, but it's extremely elegant. And
What's the name?
it's quite a name, but it's called DPLL. So
But why is it so long?
because it's the name of the people who actually come up with this, and yeah, it's fun. You know, you can. I can't even pronounce them correctly. Davis is correct. Putnam, like man, love man. Yeah, okay. Anyway, this is developed through two papers, 1960s and 1962. But I will explain later that this algorithm was actually developed through years. But the important thing is nowadays SAT solver implement these ideas, but the only difference between what is represented in this paper and the current SAT solver is the hack people put on the implementation. So the implementation is super efficient, but the idea of the algorithm is as it's presented in these two papers, which is quite old. So known today as DPLL, and DPLL is a backtracking search, exactly as you know, but it has propagation like any other backtracking search that you saw, wide search. And there are two important rules for Boolean constant propagation for DPLL that are, I'm a bit ahead of my slide, which are unit propagation and purely literal elimination. But the difference between this type of propagation with CSV is the following. In general CSV, you remember the R consistency, path consistency, and N consistency. Basically, we enforce some level of consistency while making valid assignment. So, but here, we actually do SAT preserving transformation, and with two important rules that I'm going to explain what are these transformations look like. So we backtrack, we actually branch over assignment of value to variable, like here is true and false, and each time when we make an assignment to an unassigned variable, we call the propagation rule, which is these two important rules. So one is unit propagation. If a unique clause P appears, remove not P from other clauses and remove all clauses including P. Well, if you read it like this, it seems difficult, but it's extremely simple what it says. And you should basically, instead of memorizing how it works, you should exactly understand why it's the case. What does a unique clause P is a clause that only has one literal. If you have a clause, it's P, and remember everything is in a CNF form. So if I have a unique clause, meaning that it has one literal, therefore P has to be true, right? Because this is AND. Then we can remove all clauses including P. So if I have other clauses that P appears here, we can remove them. Why is the case? Because if this P is true, therefore this P which appears in this clause has to be true, and doesn't matter really what are the other literal and assignment in that clause are. So it doesn't really matter because this clause becomes true just because of P. Therefore, we can remove, when I'm saying we can remove a clause, meaning that clause is satisfiable, and we decided already. And what else it says is remove not P from other clauses. It doesn't say to remove the whole clause, it is just removing not P. Why is the case? Because if it is true, not P is false, it really doesn't affect any decision on over other literal in that class. We can forget about that and makes the size of classes much smaller. You get the idea behind this, right? So the rule is if a unique class P appears, remove not P, and from all other clauses, because we don't care, because that doesn't help decision over that clause, and remove all clauses including P, but we can remove the whole clause that has P because we know that P is true and we don't care about the decision to the other literal that are in that class. So the idea behind it is very simple. And one important thing, when I say unique clause, meaning that it has one literal, it could be not P also is a unique clause because it has one literal, and literal is P or not P. It shouldn't be necessarily the clauses are only the positive variable, it could be negative variable. Pure literal elimination is if P occurs only negated or only unnegated, delete all clauses involving P. Why is the case? Because if P always is true, we can say P is true and remove all the clauses because it doesn't matter what are the assignments of the other variable in that clause. We can make a decision. There is no constraint that says, okay, P sometimes could be true, sometimes could be false. It's always true or always false. You can make a decision and remove all the clauses respectively because the decision is made when we assign to one clauses. It doesn't matter, right? For example, here is P. We have no clauses that negate P. That P always has to be true. Doesn't matter what are the other variables in those clauses. We can remove these clauses, meaning that these clauses are satisfiable by just deciding the P is true. Or if it's not negated, if all the time P is appear as negated P, we can say P is false, therefore not P is true, not P is true, not P is true. All these clauses are satisfiable because they become true and we don't care about the rest of the literal of that. On that clause. Is it clear? And all these things thanks to the fact that we are CNF. Because we know that these are inside the clause, there is or between literal. If there was not or, we couldn't really remove because then it was matter. It matters what would be the other literals in that clause look like. So this is not this. I'm looking for. Okay, so unit propagation example. It says that if we have a unique class P, like x5 here, we have to remove not P from other classes and remove all classes including P. We have a unique class x5. It has to be true because it's disjunction, so every class has to be true, therefore x5 has to be true. So we remove the not x5 because then it's false, doesn't matter, the decision for this class only depends on x4 because this is false. And also we can remove this class entirely. Why x5 is true, and it really doesn't matter what is the assignment to x1 and x2. Why? Because this is or. This is clear, right? So this is the unit propagation, and pure literal elimination was if P occurs only negated or only unnegated, delete all the clauses involving P. So, okay, here, it's the same example as top, right, yeah. Here, x1, we remove that, but imagine it was x1, it never negated, so x1 has to be true, therefore we can remove all the clauses easily. When I'm saying about removing, just remember, I keep repeating that, it means that the decision for that clause is made It means that that particular clause or a formula is satisfiable. So we already make a decision for this class. And for this formula, by unit propagation and pure literal elimination, we basically could remove quite a lot. And actually we could x4 is, again, we can say if x4 is true, and therefore we remove not x4 and we propagate further. I have a very big example of how we perform EPLL with these two propagation rules. So if you don't understand by now, you will understand later with a big example. We call unit propagation pure literal elimination. It's Boolean constraint propagation. It is like constraint propagation. It only has Boolean in its name. And it's extremely simple. What it does is we call a formula, just a second. We give a unit propagation the formula, and the same for pure literal elimination. And if the empty clause is in the formula, actually we have a conflict. We return therefore empty, that we know that particular assignment of value to variable in overall search didn't work. And if it's not, we return the formula, which a lot of clauses of that were deleted or decided by these two propagation rules.
The unit propagation that will work for a unit clause of not P as well as P, right?
Yes,
okay.
I just said that. Ask again, so it is unit in terms of literal, not term of variable.
Okay.
Not P, and then to be clear, also is unit literal. Okay, and how the whole DPLL works with the Boolean constraint propagation is quite simple. It receives a formula, and it's called the Boolean constraint propagation, which was the previous function, meaning that applying these two propagation rules. If it's empty, meaning that even without search, we realize that this is not satisfiable. We are good. And by good, meaning that we don't need to search. It's not good because it's not satisfiable. But if it's not empty, hopefully we have a lot smaller clauses. Still, we have to check whether the assignment is complete. Perhaps the problem is simple, and without branching over the assignment of value to variable, we already solved the problem, meaning that the Boolean constraint propagation is enough for solving the problem, which is nice. If the assignment is complete, return assignment, but usually it's not the case, meaning that still we have to choose unassigned variable and make a decision for that variable, meaning being true or false. And this is a recursive function, so we call DPLL again by variable being true or variable being false. This is equivalent of branching. It's exactly like a backtracking search, but there it was for each value inside the domain of variable. And here, since the Boolean variable, it either has to be true or either has to be false. This is how we represent it. So it's basically combination of search. This is choose unassigned variable. If you remember, this is exactly the place, for example, we could have some variable ordering heuristic. Here there are some variable ordering heuristics specific to DPLL and Boolean satisfiability. And here is the part that we have constraint, Boolean constraint propagation. Let's have an example. And I can go through this example for sure. So start with, according to algorithm, it has to go first through the unit propagation and pure literal elimination. There is no single class or a unit class, sorry, and there were no variable appears only negated or unnegated. So after applying the two propagation rule in this round, in this call of the function, we couldn't do anything. Then we get to the selecting an unassigned variable. Let's pick this one. Let's imagine it's random, or pick the first variable in the first class, and we branch over through. So x is true. So what happened? Okay. When I put this green thing behind the formula, meaning that I can remove that formula on that class, meaning that it becomes true, it has been decided. So if x is true, so meaning that I don't care about that class anymore, and I can easily say, okay, it has a lot of information. I can remove not x1 from all other clauses. Why I can do that? Because x1 is true, not x1 is false, and false in the disjunctive form really doesn't matter. It doesn't help any it doesn't help to make a decision over all clause. So I can remove not x1 from any other clauses because I know that not x1 is false. So I can remove that. But I cannot remove the entire clause because it matters what are the assignment of the value, true or false to the variable out. By this, I already get a lot of unit clause. This is the unit clause, this is the unit clause, this is the unit clause, and this is the unit clause. Therefore, I said that if I have x1 is equal to true, not x2 has to be true, meaning that x2 has to be false. It's clear why, right? The whole clause has to be true. This we don't care. Not x2 has to be true, therefore x2 has to be false. So now I can basically propagate the decision over x2 by unit propagation over all clauses. What I have to do, I have to remove all the x2 because x2 is false, and I have to remove all the clauses that has not x2, because not x2 I know that is true, then I can really decide over the whole clauses. So what happened, I know that not x2 is true, so I can remove these clauses because this is true, I don't care about this, and I can actually remove this clause because not x2 is true, I don't care about this, and I can remove this, and perhaps more. Yeah, here there is another one here which I didn't see. So, okay, another unit propagation I can do is still, I keep doing unit propagation until there is no unit clause. So, here not x3 is alone, still I have a unit clause. Not x2 has to be true, because the whole clause has to be true, meaning that x3, therefore x3 has to be false. So if x3 is false and the entire not x3 is true, by unit propagation, I can remove this one, for example, because I know that this is true, so I don't care about not x6. I can remove this one, because I know that this becomes true, I don't care about this one. I also can make this true because I don't care about this one. Perhaps if there are more x, we can see. Yeah, that would be. So again, I can still have, you see that I have not x4, not x7, not x10 for the candidate for doing unit propagation. So I keep doing unit propagation because I don't need to do branching, because there still I can do a lot more by constant propagation. And here, again, x4 has to be false because not x4 has to be true. Therefore, by the rule of unit propagation, I remove all the clauses that has not x4, which is this one, this one. I actually could remove x4 from this, not the entire clause, because I know that x4 has to be false. I can remove this one, but I can't remove the whole, because this is false. I have to still decide over x5 and x6. And I can remove the entire this clause, and this one too. I guess yeah, okay, exactly that happens what I said. Again, another unit propagation. I'm going to slow to this example because it's very important and at the same time it's simple. I want to make sure that you really understand this how unit propagation and the other constraint, Boolean constraint propagation works. And what again happened? Not x7 has to be true, therefore x7 has to be false, meaning that I can remove here x7 from this clause, not the entire clause, only this one, and I can remove the entire clause, these two clauses, because not x7 has to be true. And also this one. Guess I didn't miss anything. Again, another unit propagation, not x10, meaning that x10 has to be false, and I do the same things. So I don't have any other unit clause. I don't, well I wrote here, but still if you see, I don't see any other unit clause, and there are no variables that appears only negated or unnegated. So now when I can't perform any more constraint propagation, it's time for doing branching. So I select one unassigned variable. Here, for example, x5. I could have choose x6. This is when heuristic can help us. We can randomly. So I choose a variable that I didn't make any decision, or unassigned variable, now x5, and I make it true. If x5 is true, I can remove the whole clause, and I can remove not x5 because I know it's false, but I cannot remove the entire clause. I can remove not x5, and I can remove not x5, but not the entire clause. And then the unit propagation, not x6 becomes alone, therefore x6 has to be false. I do the same thing as I did before, and now not x8 it becomes alone, therefore x8 has to be false in order to make the whole clause is true. And then x11, and I have actually x9 again. Now here x9, x12, all both are alone. So, and what happened, I left with x12 and not x12. Well, it obviously is a conflict because if I add x12 true, I have to remove all the not x12 from the other clause, meaning that I have a clause that becomes empty, meaning that this is not satisfiable. What I have to do, I have to backtrack over my decision to x5 and make x5 as false, and backtrack what I did on constant propagation and start from here. So, but if I didn't find conflict, it was nice because I could remove a lot of things. And even though that I found conflict, still are very good, because if I didn't have this powerful constraint propagation, I have to do a lot of branching and switch between true and false, and I wouldn't back to this x5, which is in the second level of my search, quite fast. So you already see that how Boolean constraint propagation is very powerful. So, is there anyone that did not understand what's going on? assume that everyone understands. If not, I can't go through that anymore. It is long. Once really do it at home by yourself and make sure that you understand this example. Oh, great. Okay, so that's what I'm saying. It's red meaning that it's find the conflict. Now it has to go through a X file. Right.
Do you still use the other techniques from constraint CSP, like forward checking and so on, or and path checking and all that? Can that be used with SAT or?
I don't know what you mean by path checking.
What's the name for it?
So forward checking, I'm not sure, but we do variable ordering heuristic a lot. I actually will not teach variable ordering heuristic on SAT. I removed it last section. I thought it is too much, but I already put the papers that have variable ordering heuristic. I get you back to the question.
Path consistency was the name for it. Sorry.
So the path consistency in this, no, we don't use path consistency in that. All we use is back jumping. I get to that. What's called variable ordering heuristic. For the forward checking, I can't answer because I don't know. I have to check. I don't want to give you an answer which is not correct. But no, we don't use path consistency. We use path consistency and temporal constraint propagation on the part 6 of this quite heavily. We will get to that, but not for the SAT. And we use a structure base, meaning that if the problem is clustered, back jumping and variable ordering heuristic. Which variable ordering heuristic I'm not going to explain. As I said, I removed, but it's in the paper on the additional references in case you are super interested to know how is the variable ordering heuristic in the SAT look like. Which is very important to choose. If you have millions of variables, you can easily imagine which variable you pick first, you pick next. Is it x1, x5, I don't know, or x6? They're really important. No, so Boolean constraint propagation detects conflict when the clause become empty. We already see that in the example. Here, x12 and not x12 appears, conflict found, and the clause becomes empty. And when it becomes empty, the chronological backtracking goes back to the most recent branching and flip value of the variable. You already see this chronological backtracking and CSP. If you remember in the map coloring, so the example was something didn't work, I guess it was South Australia, and chronological backtracking only changed the value of Tanzania, which wasn't even connected to the actual graph. It was totally useless. So the idea there was go back to the one who actually caused the conflict, which we call it the culprit set. We have to calculate the culprit set, and back jumping goes to a variable who actually caused the conflict from that culprit set. Here is the same idea, but there I just explained the idea behind that. Here I give you an algorithm which is very elegant. I really like it. And it's called clause learning. We basically learn the clause that lead to a conflict. And while we are doing search and propagation, when we get to the empty clause, when we see a conflict, we look at what caused conflict, we learn, and we add that clause to the set of our original clause, and we start over. That's the whole idea behind it. I go through an example, we will realize how exactly that happens. But I think it's the clause learning, the idea of the clause learning what went wrong during search is the idea is quite elegant. And I will teach you a specific algorithm in the constraint, Boolean constraint satisfiability, but you can use this idea in any other search. So for example, I did clause learning for meta-constraint satisfaction for my for one planning problem during my PhD, and there of course it wasn't clause because I didn't have this representation. But I tried while doing search in a big problem, learn what it caused a conflict or potentially caused a conflict. And it helps really a lot to solve a big problem efficiently. Anyway, so, okay, clause learning, learn clauses that will avoid repeating mistakes. That's the overall idea. And conflict-driven backjumping backtracks to the culprit. And the culprit is, I go to the example of what the culprit is basically what makes the problem unsatisfiable in this case. Okay, this doesn't have anything that I didn't say. So, here's an example. So, for a second, forget about, just I want to make sure that this, yeah. For a second, forget about the unit propagation and pure literal elimination. This is an example I create only to see how, only to show you how the clause learning works. So, yeah, don't apply the unit propagation and pure literal elimination here. So, actually, I was making a mistake. Yeah, X1, sorry, X1. The first, yeah, because X1 is only appears true here. You could make it true. Yeah, okay. I'm gonna start over. So I pick X1 and assign it to false. Why? I mean, you can assign it only true or false. I pick false, doesn't matter. So if it's a bad assignment, through the search, I back jump or backtrack through this assignment. And when X1 is false, I can remove other X1 from the other clauses because it doesn't matter to overall decision of that particular clause. Here, what I'm going to show you is a bookkeeping, meaning that what is the consequence of particular assignment to another variable, and you will see how that works. And from the graph that I will create here, later I can detect the culprit. So here I assign X1 to false, and then I remove the other X1 from the other clauses, because then it's false, doesn't matter for the decision of the other variable in the class. And when I make X1 false, X4 has to be true, right? Because this is CNF, this is and between these, obviously. X4 has to be true. And X4 has to be true. Here, my bookkeeping culprit graph, it says that the assignment of X1 to false caused X4 to be true. The choice of color, I guess yellow is for those I'm branching over, and blue is for the one who is implied by that decision over branching. So then I pick another variable, let's say X3, and I assign it to true. So therefore the color is yellow. And if X3 is true, where is X3? Oh, okay, I already assigned it. If X3 is true, therefore not X3 is false, and we can remove it from the class because it doesn't matter. And the fact that not X3 is false make not X8 true, therefore X8 is false. So then we can say x3 equals true, make x8 false, therefore there is a direct edge from x3 to x8. Why I have a direct edge from x1 to x8? Because x1 and x8, where I am, x1 and x8 actually appear in the same class. So not only we have to make a direct edge from the variable that caused x8 to false, also from the variable that are shared in the same class, like here, x1 and x8. So the fact that x3 also is x3 is true, it makes x8 false, and also x12 true, right? x8 is false, therefore this one has to be true in order to make the whole class true. So x12 becomes true, and then we add a direct edge from x8 to x12 because that's the direct implication of x8 being false. Also, x12 and x1 are shared in the same class. Therefore, it has to be a direct edge from x1 and x12. I emphasize here that this graph is going to help us to find the culprit. When at certain point that we get an empty class, we find a conflict, we want to back jump to the branching that actually caused the problem. Therefore, we have to memorize enough information that help us to retract to the situation and the situation that caused that problem. So I branch over x2 and I decide x2 has to be false. So x2 has to be false. I create a node, and if x2 is false, what's gonna happen? I don't think x2 here. Here. x2 is false. I can remove that, and I can also remove other clauses that have not x2, which is no class. So what is the implication of x2 being false is x11 has to be true, right? So I add x11 is true, and you see that x11 has not appeared in any other clauses, so I think I'm good with x11. So I branch over x7 and I decided x7 has to be true. The fact that x7 it has to be true, meaning that I can remove not x7 from the other clauses, and which makes x10 has to be x7 has to be true. I can easily remove all those clauses that have x7 as true, because then also I don't care about what is the decision to other variables are. x7 can be true, and what I can remove not x7 because it's false. But what happen if I remove these two? I end up to x9 and not x9. So x7 is true, then not x7 is false, therefore x9 has to be true. So I add a node with x9 has to be true, and at the same time not x7 is false, because not x9 has to be true, which x9 has to be false. So it becomes a conflict. It creates a conflict. Here, x7 has to be true, it causes both x9, both x9 has to be false and both x9 has to be true. This is two edges. Also, we have a direct edge from x3 has to be true to x9 has to be false. Why is the case? Because of this. Because also x9 share a variable in the class with x3, therefore the decision that x3 has to be true affects on the fact that x9 has to be false. It's clear, right? It's a bit here. this is this is the node related to x1, this is a node related to x3, and this is a node related to x7. So now we have a conflict. Therefore, we have to do two things here. We have to learn what has been gone wrong. Also, we have to back jump. First, let's learn what are the clauses that cause the problem. This is a conflict, and the direct edge to the conflict variable are x8, x7, and x3. The fact that x3 is true, x7 has been true, and x8 has to be it was false. That caused this conflict. And what does the conflict? Be left with x9 and not x9 at the same time. So x3 has been true, x7 has been true, and x8 not been true. This combination of assignment implies conflict. Therefore, negation of this, not x3 or not x7 or not x8, is the clause we learned, and we add them to the set of clauses we have. And we have to now back jump to one of the branches that cause conflict between x3 and x7, which is the yellow one. We actually will not backtrack to x7, we back jump to the one in the earlier stage of the search, and we back jump to x3. So, and the rule is here between between the variable in the conflict set, you will back jump to the one is further to your last assignment. And yeah, basically it. You've done two things. You learn a class, and how you learn this by look at your conflict set or concrete set, and you negate those, and you add it to your list of your clauses, and you back jump to the variable in your conflict set that is further away from your branch. And this is basically two rules. And that's about it. I have to be good with time. Yes, I am. And I'm not going further ahead. Any question? I think these are super simple. Explaining them is actually more difficult because you have to play with, okay, this has been true, therefore this has been, the clause is already decided, you can remove it, this has to be false, therefore the other literal and the clauses has to be true. You have to do, basically, you have to do this kind of reasoning. And having, although this is so simple, but you see that already with this unit propagation, you can remove a lot of clauses, meaning that you can already decide. And that's it. If you have no other question, I guess this is a good time to end the class today. Go through this, please, and try to understand it. I can give you, these are the stuff that comes at exam. So if it makes you read the stuff. So, and as simple as this, there won't be more huge exams.
Will there be old exams available to practice on?
I will go through, I guess, one exam in the class, one by one, but I will share with you that exam before the class. And I haven't decided, but I guess either one or two exams I will share, just, but I will go through one exam. And the last session before the Christmas, that's the plan. I haven't decided I'm not sure if it's a good idea or not. I don't have any other options. It is in Java, and you will go crazy. So this is actually implementation, and it's based on the other stuff that we have implemented in ASS. So there's no Python code available even, like IMAX stuff.
The Java code framework did feel a bit over-engineered in some places, over too much, more abstraction than was needed, especially for something that's supposed to be pedagogic.
Okay, yeah.
Maybe the framework.
I agree, Python is easier, but I'm biased with Python. Therefore, if I would use Python, I will leave all the coding to you when I do that with Python.
Okay.
All these things goes to YouTube.